Acids and Bases Introduction. Now, you should be familiar with the definition of an acid. Okay, what do acids do? You're probably used to hearing that acids just release hydrogen, okay, or release this hydrogen ion. Okay, well, that is kind of true, but we're going to go more in depth. It's not just about releasing this H plus. So for example, this is a very common one. Okay, hydrochloric acid here breaking down into our hydrogen ion that we've talked about here, and obviously what's left over, its counterpart, is also going to break apart. Okay, Cl minus. Again, this one needs to be an AQ, right? This is aqueous because if this here is an acid, it needs to be dissolved in water. Aqueous means dissolved in water, okay? So if it dissolves in water, what's going to happen? It's going to be easy for it to break apart. This is why this happens, right? The H plus breaks apart easily and the Cl minus breaks apart easily. Of course, these need to stay as aqueous as well because they're all within the same container, okay, of this reaction of them dissociating, breaking apart, happening. It's happening in the same thing. So this is what you're probably used to knowing about, okay? Well, I also want you to now focus not just on this release of hydrogen, okay? By the way, hydrogen, okay, obviously has one proton, okay, and one electron. So when we lose that electron for the bonds to occur, right? If this is gone, we're just pretty much left with a proton now, right? So I want you to now think of this this hydrogen that's being released, okay, as a proton. Okay, so we have this positive, hydrogen here is pretty much like a proton from the acid, okay, from acid being now attracted to a negatively charged substance, okay? Okay, I'll give you an example here. So let's say we have, hydrogen here, we have oxygen over here, okay, and this is obviously going to be negatively charged. Okay, we can put, actually two of these here. Okay, so this is negatively charged over here. These are obviously positively charged. So this H plus here is absolutely very attracted to this negative dipole here, okay, of the oxygen. So when we have this H plus combining with our water here, what does it form? This creates a formation, okay, so it forms H3O, also known as hydronium. Okay, this here is called hydronium. So it's not just about this release of hydrogen. It's also a formation of H3O plus because this attractive force is so strong, okay, between this and this that it does absolutely create this hydronium. So this here is, it's obviously a charged particle, right? So this charged particle here, I'm just going to write this here, this charged particle formed from an atom. Okay, I know this, we don't see this as an atom, right? This H2O, not really an atom. Okay, it's like a bonded molecule. Okay, so it can be from an atom or bonded molecule. Okay, so this charged particle here that formed from this bonded molecule, okay, what is this process called? Is called ionization. Okay, so this is ionization. Therefore, what can we now update our definition for an acid? Okay, so this means an acid is, obviously it releases H plus. Okay, so it's a substance that contains H and releases this H plus. So let me reiterate here. So it's a substance that contains H, or typically contains H, okay, and ionizes. Okay, we learned what ionizes is about over here. Okay, and it ionizes with H2O, with, okay, H2O water over here to create hydronium. Now what about bases? Okay, well, bases, we got to similarly write here that even though it's a substance that you're familiar with. Okay, so we know that it's a substance that typically contains, right, this hydroxide, and rather than ionizing, we gotta say that it actually dissociates with water to create our hydroxide over here, okay? Because with our acid, it needs to ionize, okay, as opposed to dissociating. It's to ionize to create that hydronium. Bases dissociate to create this hydroxide. Because right now, so far, you've probably only seen an example for bases as simple as, let's say, you know, KOH over here. Okay? And breaks down into K plus and OH minus. And it's releasing this OH minus because there is an OH in the actual name. However, it's not always just this simple. Okay, it's not just about this dissociation yielding this hydroxide, because hydroxide was part of the actual reactant. It's not just about that. Because what if I give you an example with NH3? Can NH3 with H2O form hydroxide? Is this possible? Well, let's have a look at an equation. So we have our NH3 over here, and we're going to add it with our H2O, okay? Again, you're used to knowing that this OH minus over here got released thanks to this OH that is part of this reactant over here, this KOH. However, if I were to finish this off for you, look what happens. We actually end up getting NH4 and OH minus. Oh my goodness. This OH minus has been released just like the previous example, but we cannot use this example because guess what? This one has an OH, this one does not. So how did this OH minus over here come about if there was no OH, okay, in the original reactant, right? Because obviously you can see here that there is no OH, okay? Where did this OH go in order for this to be created, okay? So something is a little bit off, okay? What the heck is going on? So it's actually not about the OH being part of this original reactant. It's actually about the donation of a proton. So maybe I'll write this here. So therefore, it's more so about the donation of a proton and not about how the hydrogen or this hydroxide is in the actual name. What do I mean by this donation of a proton? Well, we've already established, right, just recently that the H is pretty much like a proton. So if there is a donation of a proton, do we see any of that happening with this one or this one? Well, look at this NH3 over here. Its counterpart here is NH4. Did it receive an H? Did this guy here receive an H? Absolutely. It had 3 over here, but now it has 4. So this means that this one did not donate a proton, but this actually got a proton. It received a proton. How about this H2 over here? Its counterpart over here. It absolutely looks like it lost the proton, okay? Because there were 2 here. Now there's only 1. So this here was donating the proton, whereas this one here received that proton. Let's have a few look at some examples. So I want to iterate that for a base, it's more so about a substance accepting an H plus or accepting a proton. So for the base, it is accepting the proton. In contrary, for an acid, it's going to be the opposite. It's going to be a substance that donates. Okay, the H plus, or donates the proton. Now, before I show you how this works out in action, where acid donates and then the base accepts, I want to star here that if a substance behaves basic, another substance must simultaneously, at the same time, act acidic. Let me show you what I mean by this. Let's get that same example I just showed you in this video, and let's solve it by identifying the two conjugate acid base pairs. So let's look at this NH3 over here. As we can see, its counterpart here, like I said, has received an extra proton. Okay, it received an extra hydrogen. And this one here, it, as you can see, lost that extra hydrogen. So this 2 is now a 1, okay, as a subscript down there. I want you to always have in the back of your mind, when we deal with a conjugate base, okay, what is occurring? Well, when you have a conjugate base, it must be acting with an acid, okay, as a counterpart. What does it say up here? If a substance behaves basic, another substance must simultaneously act acidic. So if we have a conjugate base, it is in accordance with its acid. So the conjugate base of an acid is what is left over, what is remaining after this hydrogen was removed. Okay, so I'll just put it in layman's terms here. What is remaining? Okay, what is remaining or left over after a hydrogen was removed? Okay, and again, this is in accordance with an acid. Okay, so the conjugate base of an acid, what is remaining after the hydrogen was removed? Okay, so that is going to be a conjugate base. For a conjugate acid, for a conjugate acid though, so the conjugate acid of a base is what is forming when a hydrogen was added to it. After a hydrogen was added. I'm going to keep these two disclaimers here on the side as we try to solve this question over here. Let's first deal with our conjugate base. Okay, we got to find this. Okay, what is remaining after a hydrogen was removed? Okay, obviously this here was where the hydrogen got removed. Like I said, there was 2 over here, now there's only 1 over there, so this must have been the acid, because a conjugate base, okay, which is of the acid, okay, so the conjugate base is what is remaining after the hydrogen was removed. So after this hydrogen got removed, what is remaining left? Okay, this is what is remaining left. So this is obviously the conjugate base. Okay, So conjugate acid, however, is in accordance with the base. Okay, so obviously if this is an acid, this has to be the base here. Okay, so this is quite obvious. This is quite obviously the base. Okay, but just to finish this off, okay, the conjugate acid of that base, of this base over here, okay, is what is formed after a hydrogen was added. Okay, so we had 3 over here, now we have 4 over here. Okay, so this hydrogen got added over here, so this here is the conjugate acid. Let's try another one. Identify the 2 conjugate acid base pairs. Same thing. Let's look for what was remaining after the hydrogen was removed. So as we can see over here, compared to what it became, look, there was an H before, there is no longer an H here. Okay, so it obviously went away. That H went away. Okay, so what is remaining after the hydrogen was removed? So this is obviously belonging to this, right? This description belongs to this one here. So obviously this here is the conjugate base, and it was obviously in accordance with its particular respective acid, and this is where it came off from. So this was its respective acid. What is the conjugate acid? Okay, it is what is formed after a hydrogen was added. Hydrogen was here, as you can see, got added over there. So this is obviously the conjugate acid in accordance with this, its base. Before I show you how to do this one here, can you please take a minute or two and try this on your own and attempt it, because it may be a little bit tricky, maybe a little bit confusing before I break it down for you. Okay, hopefully you tried it. What is going on? Okay, so this O here, as you can see on this side, there was an H that got added. Okay, however, what's tricky though is that there was an H over here. It had 2 of them and it got removed, as you can see, because there's only 1 of them now, right? It got removed over here. So what the heck is going on? Well, let's just follow suit. This here had an H. Okay, so this here didn't have an H, but this one has an H. So an H got added. So what is formed after a hydrogen was added? This here is a conjugate acid. Okay, in respect with this one over here, which would have been the base. Okay, however, this could also be the conjugate base. Why is this the case? Because this one here has only 1 H. This one here had 2 H's, which means this actually removed, right? An H was removed here as well. So that belongs to this description too. What is remaining after a hydrogen was removed, right? There was 2, now there's only 1, so it was removed. So this here is also a conjugate base, and that's in respect to this one here, which would be the acid. So technically, this is the answer. Alright, these 2 here are the green questions of the day. This is the first one, this is the second one. Please pause the video, give this a try on your own, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.